Hello, everyone, and welcome to our live session for today, July 17th, 2025. My name is Matthew. I work behind the scenes and I'm one of our course staff. Welcome to our live session today. For those of you who are joining us from our classes, we are happy to see you here in real life, sort of online. And for those of you who are joining us from elsewhere, thanks for finding us. Let me go over the sort of the way that we proceed with these live sessions, and then we'll get to your questions. For those of you who are new, please post your questions in the chat. I will grab them from there, and I see all the questions. Please ask your question only once. I do see all of the questions, and I'll grab them from there, and I will moderate. I'm going to pick questions generally in the order that they're asked. But I will also jump around sometimes to give a variety of people chances to have their questions answered and to cover a variety of topics. We also try to keep this at a beginner level. This is an introductory level discussion. So if you have super advanced questions, there is probably a better venue for that. We will hit these questions. I'll ask them to Chris, and then we'll go through and answer those. Usually we start with a topic that Professor Impey proposes, and then people can ask their own questions, or they can riff off of Professor Impey's topic and start from there. So with that introduction, Chris, why don't you welcome everyone, and then we'll get started with the questions.
Okay, good to have everyone here. We'll just get going, jump right in. The topic I wanted to bring up at the beginning is a news story from just a day or so ago. And it's about why the universe contains matter and not antimatter. And that may not be something you've thought about or considered, but the laws of physics are essentially symmetric between matter and antimatter. They can be created equally easily out of pure energy. And in the early universe, it's likely that because of the intense energy in the Big Bang, particles and antiparticles existed at essentially equal numbers. If they'd been exactly equal numbers, then those particles and antiparticles would have annihilated, leaving only radiation, pure radiation, and the universe would have not had any stuff in it. There would be no people, no planets, no stars, no galaxies. So it's a pretty profound issue, the fact that there was a very slight asymmetry, about 1 part in a billion, which meant that there was a slight excess of normal particles over antiparticles, such that after the annihilation happened, a small residue of particles formed into the material contents of the universe. And the question has always been why? What was going on then? A clue about the why has come from the Large Hadron Collider at CERN in Geneva. And this is the news story from just a day or so ago. Because they've seen an asymmetry in the particle decays when they smash particles together in the Large Hadron Collider. So the technical term for it is charge parity violation, CP violation. It's been known in physics for over half a century, but they found a new form of it involving heavy particles, or baryons, the stuff of most of the material of the universe. At a very small level, a very small asymmetry of only a few percent, based on maybe 100,000 collisions they observed, but it's quite a significant result. And so it's a hint as to why nature has this skewness built into it at the level of fundamental physics that could have led to the matter-antimatter asymmetry and the dominance of one over the other by a very slight amount. It's not solved the question, unfortunately, because the standard model of particle physics doesn't really give you an easy explanation for what was happening in the early universe. So people have had to reach to grand unified theories to explain this, what went on in the first fraction of a second after the Big Bang. And we don't have grand unified theories yet. Those are not in the standard model of particle physics. So all that's been seen really is a hint of the kind of physics that would be required to explain why the universe contains stuff and not anti-stuff. It's an interesting story. It'll probably take a few more years to play out before we know the answer, and before we know whether the physicists have essentially resolved this cosmological issue, and also whether the solution they find involves new extensions to the standard model of particle physics, which would be very exciting for them.
Excellent. Well, thank you very much for that introduction. So we will start with some questions that were already in the chat. And if people have questions related to this topic, please post those in the chat and we'll grab them from there. The first question is from Terrence Jacubus, who asks, Professor, Proxima Centauri is the closest binary star system to our sun. This red dwarf star was discovered and there has been at least one confirmed planet. The question is there oxygen present at Proxima b?
Right, so Proxima Centauri is indeed the nearest star system, and so if you're going to find a Earth-like or habitable exoplanet, it would be a very exciting place to find one. And there is indeed at least one moderate size, so terrestrial, rocky exoplanet in the Proxima Centauri system, and people are looking hard for others. The question of whether that planet has oxygen, which might indicate life, that's called a biosignature, and that's the classic telltale that people are looking for to indicate life. That has not been an observation that astronomers can attempt yet, because even though it's the nearest star system, the planet is extremely small and extremely faint. It's 100 million times fainter than even that red dwarf star. And so there are no current observations able to look at its atmosphere and inspect it for gas molecules like oxygen. It could, and James Webb is probably not sensitive enough even to do that from space. It's probably going to take the upcoming generation of 20, 30 meter telescopes that are under construction to do that difficult observation, but it'll probably be one of the very first things those big telescopes do when they're commissioned.
Excellent, thank you very much. The next question is from Adrian Murray, who asks, is the missing matter in the universe hydrogen gas clouds that surround galaxies?
There has been progress on the missing mass issue in the universe when it comes to normal mass. So we know that dark matter is out there, and dark matter exceeds normal matter by a factor of 6 or 7. It's about 24% of the universe as opposed to 5 or 6% for normal matter. But the question of the normal matter still exists because all the stars and all the galaxies only account for about 20% of the normal matter. So we've been missing most of the normal stuff in the universe. Forget about the dark matter. And this seems to have been resolved by radio astronomers in the last few months, where they've made observations of how radio pulses travel through the diffuse regions of intergalactic space, and they've seen signs that intergalactic space, that very diffuse medium, very, very low density, but very high temperature medium between galaxies, does indeed contain most of the normal stuff that we expect to see. So most of that normal stuff, again, is not in the form of stars composed into galaxies, but is in very, very diffuse and very hot gas. So this is a very interesting result because it sort of nails down a component of the universe that people have been looking for decades.
Excellent, thank you. The next question is from Ben Tennyson, who asks, good morning, Professor. I completed your course on Coursera a week ago and would like to continue learning. Could you please suggest what I should do next?
Sure. I mean, we have the introductory course, but we have 2 other courses which don't cover exactly the same ground, but go in different directions. So we have an astrobiology course on Coursera, and that's much more along the lines of exoplanets and solar system and how do we find life in the universe. So that's a natural follow-up to a general astronomy course. And then we have one that we launched the most recently called The History and Philosophy of Astronomy. And that delves more into the history, as the title implies, sort of deep history of astronomy going back thousands of years, and also the philosophical issues that are raised, many of which come out of physics as well as astronomy. So you can go look elsewhere, of course, for online courses. There are many good online courses out there, maybe at higher level than an introductory one, but we have 2 MOOCs that might interest you.
Excellent, thank you very much. And there's a link for those MOOCs If you scroll all the way to the top of the chat, I posted that, and I can post that again. So you can find those. It's the main landing page for the University of Arizona courses, and you can click on that and find the rest of our courses there. The next question is from one of our live participants. Remiss Guide asks, my question is, if two Kerr black holes collide with each other, what happens to each of their respective ring singularities? So maybe you can talk a little bit about what a Kerr singularity is and what would happen if those collide.
Yeah, if you have a rotating black hole in the Kerr solution, that was the first full general relativistic solution for a rotating black hole, then in the rotating black hole in general relativity, the point singularity, the zero-dimensional singularity at the center, gets turned into a one-dimensional ring. If two Kerr black holes collide, that's an interesting question, two spinning black holes collide, and we see evidence, of course, of this. What LIGO is detecting when it detects black hole mergers involves black holes that almost all are rotating because they're from collapsed stars that had angular momentum. So LIGO is actually measuring these collisions every few weeks. So when the black holes merge, then the masses redistribute, and at some point there's instability, of course. The mass doubles, or the mass becomes the sum of the two masses with some amount released as gravitational waves, so there's a little loss of mass. And the best guess within the theory of general relativity in simulations is that the ring singularity continues, that in the spinning result of the two black holes, each of which was spinning individually, this ring singularity is maintained and will eventually stabilize into a stable orbit. But that's speculation because we cannot inspect within the event horizon. So it is pure theory and pure simulation that suggests that. The black hole observations, even with LIGO, do not really give us evidence of what's happening to the interiors of the black holes after they collide.
Excellent. The next question is from Adrian Ionescu, who's on with us live. The process of electrons absorbing and emitting photons is very puzzling to me. The electron is a point-like particle without structure. How can I understand this process?
Well, electrons can scatter photons. They are indeed point-like, but they have electrical charge. So there's an electrical field, and electromagnetic radiation is composed of oscillating electric and magnetic fields. So the easiest way to understand the interaction of an electron and a photon, or an electromagnetic wave, is in terms of the interaction of their electrical fields. Because the electron does have an electrical field, an electrical charge that extends beyond its point mass. And so it's this interaction between the electrical fields that explains electron scattering of photons, which is a very fundamental physical process.
The next question is from Saad, who is on with us live. Hello, Professor. It's difficult to imagine that there was no time and no space before the Big Bang. Can we assume that the singularity was in a dimension other than the 4 dimensions that we know? Or what's the best way to sort of picture this in one's mind?
I mean, a singularity is a cryptic entity in physics or in science because it has 0 dimension, has infinite mass and infinite energy density. So we shouldn't pretend we understand the singularity. That's the first thing. Physics does not understand it, cosmology does not understand it, and so really even speculating about it has limited validity. Whether it involves extra dimensions, as string theory might suggest, that will depend on whether string theory is a valid theory of physical nature and the universe, and the jury is completely out on that. So at the moment there's no evidence that you need to appeal to extra dimensions to understand the Big Bang or the Big Bang singularity. It could still indeed be just the 3 dimensions of space and 1 of time that we're familiar with in our present day universe.
The next question is from Tanya, who asks, how reliable are philosophical ideas in theoretical physics? Can they be an inspiration and contribute to the discovery and development of new physics?
There's an interesting relationship between philosophy and physics. Remember that physics used to be called natural philosophy. I think at the University of Cambridge in England, until the 1970s, the degree in physics, the bachelor and the PhD in physics, was called a degree in natural philosophy. So the subject was called natural philosophy for a long time. It is natural philosophy. It's understanding nature, and the philosophy part means you can ask hypothetical questions, you can make conjectures, you can propose or idealize experiments that might be created or carried out and might not be created. And these are valuable tools for understanding the universe. The physics community has a tradition of this going back to the early 20th century called thought experiments. Gedanken experiments in the German, because Einstein used this tool quite frequently. And thought experiments are essentially philosophical endeavors because they're imagined experiments that you don't necessarily need to carry out, but which by posing them, you elucidate some issue of physics or some issue of the natural world that you can understand. In the end, progress is made by observations and experiments. Science is empirical, fundamentally. But these philosophical tools, these thought experiments, these questions we can ask, these hypotheticals, counterfactuals even, they're all valuable and they play a part, especially in the subject of physics.
Excellent, thank you very much. The next question is from an email that was sent to us by Carol Bodderton, who asks, why is a planetary nebula called that? And why haven't astronomers changed the name?
Astronomers are very traditional. You know, they don't change their ideas very quickly. They are quite attached to tradition, and they actually view that as a feature, not a bug of the field, that we have that tradition. Planetary Nebula got their name a long time ago, over a century ago, because when observed through the modest-sized telescopes available in the 19th century, these appeared to be small, fuzzy objects that were extended, just like planets are. That's how planets are distinguished from stars in the night sky. And so these objects, seen as extended, were possibly nebulae, and they were possibly planet-like. So planetary nebula was a sort of tag word or descriptor given to them to describe the fact that they were not point-like. And they were sort of planet-like in their appearance, but they were probably made of hot gas, and therefore they were nebulae. So that's the historical origin of the term, when we didn't really understand what they were. And in the modern era, of course, we do know now that they are a late stage of stellar evolution, where an envelope of gas is blown out into space and is illuminated and ionized, and it's the glowing gas that we see. And they can be circular or viewed in great detail through Hubble and telescope, for example. They have braided structures or toroidal structures or spiral structures. So planetary nebulae are not all spherical or round in shape. But for various traditional reasons, astronomers have never jettisoned the name, so they still call them planetary nebulae.
The next question is from Adrian Murray, who's on with us live. Does the religious idea of I'm not sure how to say this, hazy-chasm or uncreated light have anything to do with the theory that matter is simply congealed light?
I'm not familiar enough with the religious idea to comment on this. How do you spell that?
Hesychasm.
No, I'll pass on this because I'm not familiar with that religious term.
Okay, sounds good. The next question is from Remy Script, who asks, good morning, Professor Impey. Is the singularity point of a black hole just a point of infinite gravity, or can it be that energy is maybe stored at the center of the black holes?
In the physical description from general relativity, the singularity is a point mass. It's not necessarily an energy concept, it's a mass concept. And so when you're describing the mass distribution within the event horizon, the theory of general relativity predicts a spike or a cusp or a singularity of infinite mass density at the center. It's a prediction, it's a theoretical construct, and it's actually not fully going to make sense, because infinite mass density is not a sensible physical concept, and it sort of means we don't fully understand black holes. But it is indeed a cusp of mass and not of energy.
The next question is from Sandra Gibson, who sent an email. When you measure time in the very early stages of the universe, would the extreme density and by extension gravity of the universe slow the passage of time down?
Yes, time in the early universe has different framing than it does presently. It's an interesting question how we define time. Physics has an idea called conformal time, which can apply in different space-time situations. It's a way of measuring time in complicated space-time scenarios. And in the early universe, time, the measurement of time, is very tricky because there are no clocks. There are no standard clocks. There are no atoms to decay, for example. We use atoms decaying as a way of measuring time in the modern old universe. That's our way we measure time, or oscillations of atoms. But we don't have atoms in the early stages of the Big Bang, and so that's not a way of measuring time. So the cosmology creates its own time. So there's sort of cosmological time defined within the context of an expanding universe model that describes how time flows in these very early phases. And that's what it means when someone talks about the first fraction of a second after the Big Bang. It's a definition within a relativistic cosmology.
The next question is from Ben Tennyson, who asks, is it possible to eliminate the idea of a creator?
It's possible because it's not required in physics or astronomy. Scientists, whether they might hold personal faith or religion, are supposed to be agnostic about original causes, unless you have a physical argument, a logical physical argument that you can provide evidence for, then you can't really talk about causes. And in fact, in the terms of the universe, the Big Bang Theory does not postulate a cause. Now, whether that in some minds leaves room for a creator, perhaps, but it's not a necessary hypothesis. And so that's probably the best way to think of it.
The next question is from AKA The Best, who asks, what would happen to the fabric of space-time if a black hole was somehow traveling at 99.9% the speed of light?
That would be an interesting situation, of course, because a black hole, and we can imagine situations, not at that speed, but there are situations where black holes, for example, in the center of galaxies or in binary or triple systems, can suffer enormous ejection velocities or get kicks to significant fraction of the speed of light, but probably only 5 or 10% of the speed of light. So a black hole traveling at a very high speed through space-time will, of course, induce effects in the space-time. It'll leave a wake. It'll create a enormous flood of gravitational waves. Well, those are the ripples in space-time that result from black hole mergers. So a black hole traveling very fast will create its own gravitational waves as it travels through space, and that will probably be the most obvious signature of a relativistic black hole traveling through space-time.
The next question is from Brendan, who asks, has the Webb telescope had successes or met expectations that we don't hear about all the time in media about those achievements? So for example, are there other significant achievements that might be a little bit more, sedate or mundane, but have importance that the Webb telescope has contributed to?
Yeah, absolutely. The James Webb Space Telescope has been working smoothly for a couple of years now, and the things that make the headlines or the newspaper stories are really two categories. They're either observations of very exotic objects, or difficult observations like atmospheric detections of exoplanets, the things that might eventually lead to life detection, or they're just beautiful pictures made in the infrared with the telescope. the James Webb Telescope is working on all sorts of science, from stellar astrophysics to studying supernovae to studying normal galaxies, their structures, their interiors, their black holes, and to, of course, trying to measure the most distant galaxies in the universe. So there are dozens of research projects going on with this Webb telescope every day, pretty much, and only a fraction of those will generate a newspaper headlines, just as the Hubble Space Telescope is also working on dozens of projects at any given time, most of which don't make the news.
The next question is from Ephanog, who asks, does a Kerr black hole emit energy or radiation while spinning?
Yes, a spinning black hole is not emitting energy necessarily. Well, it's doing two things. It is emitting energy, or it's radiating, according to Stephen Hawking's idea. So it's emitting Hawking radiation. And that's a very feeble energy that it corresponds to very slow evaporation of the black hole. And for a normal stellar mass black hole, that radiation energy or equivalent temperature is a billionth of a Kelvin, so a tiny, tiny amount of energy. Probably more significant, though, the black hole is emitting gravitational radiation or gravitational waves, and the spinning black hole will be emitting quite a copious amount of gravitational waves that can be detected. Now, LIGO, the gravitational wave observatory that's had enormous success, has been looking at the most spectacular events and the biggest signals that it can detect, which are black hole mergers. But individual black holes spinning do emit a field or a sort of low level of gravitational waves that are much harder to detect, but they're certainly part of the prediction of general relativity.
Next question is from Balet Copelia, who asks, what does being able to detect gravity waves mean for science? As in, what do we specifically learn from them?
What we learn is that a very fundamental prediction of general relativity is valid, because this is a prediction that came out of the theory over a century ago, and until the last decade or so, we did not have direct evidence for gravitational waves. There was indirect evidence that did lead to a Nobel Prize in a binary pulsar to Hulson-Taylor a few decades ago. But we've learned that general relativity is a very accurate theory of gravity. We've learned how to test it in new ways. We also, from the gravitational waves, have pretty much proven that black holes exist, because the black hole merger events that LIGO has seen, now dozens of, perhaps 100 or more now, can only be explained in terms of black holes. So for people who doubted that black holes exist, those signatures of gravitational waves are stunning affirmation that black holes really exist and that they have the properties that were imputed to them by general relativity.
The next question is from Jennifer, who's on with us live, who asks, will we have another mini moon orbiting the Earth as we did in 2024? Can you talk a little bit about what mini moons are and why we pick these objects up and then they go away?
Yeah, there's interstellar objects and Earth-crossing asteroids and near-Earth debris, and occasionally it comes close enough to the Earth to go into a captured orbit. It may not be a stable orbit, so it may just last a little while and it gets perturbed and it gets kicked out of the system, or potentially could fall into the Earth and just collide with the Earth, probably harmlessly, because these are small objects and the Earth is big and most of it's ocean and uninhabited. So we can't predict these incidents of these mini moons, because objects that small, tens or hundreds of kilometers across, smaller than a typical beefy asteroid, are very hard to track and catalog. So we really only see them when they're getting close to the Earth. And so yes, I think we can statistically anticipate the presence of one or more mini moons in the next few decades, now that we have the tools to monitor things that are that small.
The next question is from one of our live participants. Ben asks, does quantum mechanics work on biological life, or are classical mechanics enough for this level?
It's a good question, and it turns out that quantum mechanics or quantum theory is required to understand modern biology. Of course, it's definitely true at the level of the chemistry and biochemistry, so the biological chemical processes, because quantum potentials and tunneling effects and quantum mechanics in general is required to understand how chemicals interact. And since some of the major metabolic processes or energy storing mechanisms such as ATP in biological systems involve the details of the chemistry of how these chemicals interact, then you need quantum mechanics and quantum theory to understand them. So yes, quantum mechanics is a foundational part of modern biology at the level of the way individual biomolecules work.
The next question is from Tanya, who sent an email, and she just has some confusion about space-time curvature. So I'll ask the question, and we can go into some detail about that, pick it apart if necessary. So the basic question is, what causes the curvature in the fabric of space and time? On Earth, we can demonstrate this with the example of a massive ball on a trampoline, where the curvature is caused by Earth's gravity. But what causes the curvature in space-time where there is no external gravitational force acting on a massive star?
So in the larger universe, the curvature of space-time is caused by the mass of the universe itself. So just as an individual object will distort and cause space-time curvature locally, then the mass of the universe, an enormous number, of course, the number equivalent to hundreds of billions of galaxies, over that very large volume of the universe will exert space-time curvature too, by exactly the same mechanism, by general relativity. So that's the method, that's the concept, that you can have space-time curvature on a cosmic scale caused by the cosmic amount of mass in a particular volume. It turns out the curvature caused is very slight because space-time on large scales is very close to flat. But it's not necessarily zero. It's just very hard to detect that curvature because it's quite subtle.
The next question is from Cosmic Conversations. Since our universe is expanding and everything seems to be moving apart, could it be behaving like a white hole? Do you think white holes might be real, and could our universe actually be one?
I think you can understand space-time expansion without invoking white holes. So I'll just set aside the white hole part for a minute. Our space-time expansion is completely understandable in terms of the cosmic history of the universe from an initial hot dense state in the Big Bang, and now billions of years later, almost 14 billion years later, we see space-time expanding and galaxies being carried apart by that. This does not have the character of a white hole. A white hole is a theoretical concept out of general relativity that's never been observed, a sort of source of energy caused by distortion in space-time. And it's a local phenomena, whereas the expansion of the universe is a global cosmic phenomena. So they're really quite different things.
The next question is from Anjali, who asks, before the Big Bang, space was a vacuum. So how did the energy come about to start the heat of the universe and create that first energy?
So it's a good question. I mean, the trick is in that first phrase, before the Big Bang, because that's not a concept that we have in modern cosmology, because we don't have a theory to describe the state of the universe before the Big Bang. However, we do have potential mechanisms to explain where the energy required to cause that expansion and then the creation of the billions of hundreds of billions of galaxies eventually in the universe came from, and that's from the vacuum. The vacuum is not nothing in physics. The vacuum has a small amount of energy. We can see that in the lab. That's been known for a century. And so the vacuum is a source of potential energy. And from that energy of the vacuum, you can borrow energy and create particle-antiparticle pairs, which come in and out of existence all the time. That's another physics phenomenon that's well studied in the lab. And so the universe is a grand version of this, where potentially out of a very early vacuum fluctuation state, you can borrow enough energy to cause the cosmic expansion and then fill the universe with energy and then matter eventually. It's cosmic creation, a quantum fluctuation that leads to the quantum creation of the universe. Now that's a general description. The physics of that is not yet attainable to us because it would require unification theory for all the forces of nature, which we don't yet have.
The next question is from Akash, who asks, could we practically harness dark energy from dark matter? Would it be possible to wipe out the problem of exhaustible energy?
So it's interesting thought, is dark energy of any use? It's a cosmic phenomenon. And unfortunately, the answer for the moment is no. It does not seem to have any practical implication or practical use, because dark energy is a cosmic ingredient of the universe that causes space-time to expand at an accelerating rate. So it's distributed over a very large scale, and it seems to be uniform. Dark energy seems to have the same strength in every direction we look, and going back in time as well. Because it's distributed through the entirety of the universe, it's not localized enough in a way that we can tap it as, say, an energy source. Because this amount of vacuum energy that could cause accelerating universe is actually very, very small. So there are two practical problems. The amount of energy in any region of space is very small, and it's completely uniformly distributed, so there's no way to tap it. So unfortunately, no, dark energy is not a solution to our energy problems.
The next question is from Arif Rooney, who asks, how can everyday people use AI to help NASA find new planets with tests? And before you answer, I'm just going to say that there is a Zooniverse project so that people can find, it's called Planet Hunters. They can use test data to find planets. So, maybe you can talk a little bit about how AI could be used, or how these sort of crowdsourced projects work.
Yeah, I mean, professional astronomers are using AI to help find planets using tests and even Kepler data that they're still massaging and trying to extract subtle signals from. So the professionals are already doing this, and if you're a citizen scientist working with the test data you can have access to, you can do the same thing, because this is open access data, and so if you capture it on your computer, you're completely free to use your own AI tools to analyze it. So some of the analysis by citizen scientists of test data is just done visually, looking for subtle signals just by eye. But you can easily use a sophisticated algorithm or AI methods, and so the people who put these projects together do not prescribe how you should deal with the data, and so you're welcome to use AI methods, and they have proven to be quite powerful in the hands of professionals.
The next question is from Thomas, who sent an email. Hello, Professor Impey. Is it possible that the reason antimatter is not so prevalent in the universe is because it's contained in black holes?
That doesn't seem to be the case, because we have not seen any evidence of antimatter on large scales. In other words, if a black hole was made of antimatter, then it must have formed from a massive star that died with a supernova and left behind a black hole. So you would have had to start with a very large star made of antimatter, and that star would have exploded as a supernova, sending that antimatter, a lot of it, into space, and that antimatter then would have reacted violently with the ambient material to create annihilations of gamma rays. In other words, we would see enormous telltale signatures of gamma rays if some black holes were made of antimatter from their precursor explosions, and we have no evidence of that.
All right, the next question is from one of our live participants. Tanya would like to know, what role can bioinformatics play in the field of astrobiology, and how important is it?
Well, astrobiology is a sort of young field. Bioinformatics is a mature field and part of biology for dealing with the information content of biology and biological processes. Astrobiology, unfortunately, is in its infancy, and so we don't have examples of biology elsewhere to study. If we did, bioinformatics would play a big role. But at the moment, we're busy looking for the second instance of life beyond Earth, and we haven't found it yet. So all that lies in the future.
Robert S., who's on with us live, would like to know if the Big Bang was a Big Bang going in all directions spherically, shouldn't it be possible for us to identify objects older than the Big Bang?
No, because if you look out in space in any direction, you're looking back in time. And so as you look out in space, and this is what James Webb is now doing, taking us back within 100 million years of the Big Bang, you look out in space, you look back in time, the universe is a time machine, and you eventually are looking back towards time zero. So there's no actual way to look before the Big Bang or to longer times ago than the Big Bang, because as you look, all you are doing is rewinding the clock towards the initial singularity and getting as close as you can with observations. So there's no before that's going to come out of that work. You're just dealing with data that started with the Big Bang.
The next question is from one of our live participants. Let's see. From Robbie asks, is it possible that we might not be able to detect dark matter because real matter is acting, or visible matter is somehow acting as some kind of a Faraday cage or somehow masking the signal?
I think that's not likely to be true because dark matter and normal matter are distributed spatially on quite different scales. So normal matter has tended to collapse into the form of stars and galaxies, and it's collapsed in the middle of dark matter halos that are much larger and more extended. And so dark matter is spatially much more widely distributed than normal matter. So there's no way to use normal matter in any manner to hide dark matter, since most of it is measured and visible on much larger scales than the normal matter is structured.
The next question is from Learning Lessons, who asks, is it possible, or would it be possible to study space-time itself as it wraps itself differently around the Earth to look for information about, theories of the universe? Like, can we somehow study space-time as it's, as it is close to Earth and warped by the Earth?
Yes, and this is a classic experiment that was done a few decades ago, actually. There was a NASA mission called Gravity Probe B. It was not as famous as some of NASA's missions. And Gravity Probe B used extremely sensitive gyroscopes from an orbiting satellite, the Gravity Probe itself, to look for the distortions of space-time caused by the Earth itself and by its spinning of which creates a torsion in space-time, a spinning of the reference frame. And it measured both things, so it was a very profound affirmation of general relativity in a situation of pretty weak gravity, because the Earth's gravity is quite weak. Gravity Probe B's data was very difficult to analyze. It didn't quite live up to all the hype of its precision, and it took almost a decade for the team to analyze it and publish the results. But in the end, it did measure the distortion of space-time caused both by the presence of the Earth and by its rotation.
The next question is from one of our live participants. Can you talk a little bit about what does extended mean in the context of stars versus planets when viewing the sky?
Extended just means distributed over an angular scale. So in astronomy, the main distinction is between something that's unresolved, which is just to say that it looks like a point source, which is to say that your telescope, whatever you're observing as a telescope, has a minimum angular resolution to do with its optics, and that's the smallest angular scale you can observe. And something that's physically smaller than what that angular scale represents on the sky will be unresolved and therefore a point source. Something that's bigger than that will be resolved, and so will seem to be distributed like a disk or over 2 dimensions. And so it's basically a difference between something that's resolved by your telescope optics and something that's not resolved.
The next question is from Arif Rooney, who asks, astrophysicists use detection methods like transits and radial velocity to map the diverse populations of exoplanets. Can you talk a little bit about the diversifying process of the exoplanet discovery process and the current population? Like, where are we now in terms of detections and methods and finding different sized planets?
Yeah, there's been a shift over time in the nature of the detection methods. The first few hundred exoplanets were all found by the Doppler or radial velocity method. And then, especially with the Kepler satellite, the vast majority of current confirmed exoplanets came from the transit method. And that's still true. Transits produce more exoplanets than the Doppler method. Especially as people push towards lower mass exoplanets, because it's very difficult to use the Doppler method to detect something that's Earth mass or smaller, whereas transits can detect something that's Earth-sized or smaller quite easily, and have done so. The third method that's actually quite important and maybe hasn't produced the lion's share of exoplanets, but it's very important because it has a great sensitivity to low masses, down to Mars mass or Mercury mass even, is gravitational lensing or microlensing. That's a statistical method because you can't repeat the observation and follow it up as you can with Doppler and transits. So microlensing has probably only found 100 or 150 exoplanets out of the 7,500 that are cataloged. But it's very important because it gives you a statistically unbiased sample and gives you reach to the very low mass exoplanets. So those are probably the three primary methods and how they balance out in the detection.
The next question is from Terrence, who asks, it takes 4 light years for humans to travel and arrive at Proxima B. On Earth, how many years would pass if we are traveling, say, at different velocities of the speed of light, so like either at 80% or like 20%.
Right. I mean, so there's a feasibility issue. The plain truth is that the idea of relativistic travel to the nearest star is perhaps on the table or on the cards for miniature microprobes, nanobots if you like, very small spacecraft. It's not on the cards for humans. The energy cost of accelerating even a single human in a spacecraft to 80% of the speed of light is more than the energy usage of the entire planet for a year. So that tells you that it's not going to happen anytime soon, even if we had the technology. If you could accelerate humans to say 80% of the speed of light, then the relativistic time dilation indeed means that their body clocks and their space clocks would run slower than clocks held back at Earth. And in the extreme of, say, 95 or 99% of the speed of light, those humans would barely age on that trip to Proxima Centuri, while time had passed at about 10 times the rate back on the home planet. So that's how the hypothetical would work, but unfortunately it's not a practical experiment we can do.
The next question is from Wendy, who sent an email. Is it thought that Saturn's moons, the water on Saturn's moons, came from comets like Earth's water? And if so, what does that say about the abundance of comets in the early solar system?
The water content of the moons of the giant planets is an interesting question, where it came from. And it is indeed the case that the best place to generate the water, the best origin of the water, is from the Oort cloud. That is the comet cloud, which contains roughly 1 trillion objects of a few kilometers in size out at very large distances. So even the input and deposition of a tiny fraction of those onto moons or planets will carry a lot of water with it. So yes, that is the speculation, that the water content of even the moons of the giant planets did originate from cometary material. But unfortunately we have no way to prove that, because we'd have to generate samples from those moons, physical samples, bring back to Earth, or possibly spectroscopically analyze remotely, but that's, don't think, good enough information to resolve the hypothesis.
The next question is from one of our live participants. In a time of deep NSF and NASA budget cuts, how do you sort of confront the limits of science funding and progress?
Well, we were busy fighting the battle. I had an op-ed published on The Hill, an online political magazine yesterday, arguing that NASA's budget cuts would be disastrous, and there's a lot of astronomers pushing back against the NASA and NSF budget cuts. The dust has not settled on that. The president's budget proposed very deep cuts to NSF and NASA science of order 50% in each case, which would really devastate the science funding in the United States overall. But Congress has shown some sign of pushback. The Senate committee that adjudicates these appropriations has, in the initial instance, proposed more or less flat funding for the federal agencies, which would be a great success given the budget cuts that are on the table. But the budget processes are a long and slow one, and it's a very messy business, a lot of politics, a lot of how the sausages get made that we don't want to think about. And it will not really be resolved until probably October.
The next question is from John, who has kind of a question about the term universe. The universe can't expand if it is everything, but if it isn't everything, then it really isn't the universe. And doesn't the word universe kind of, isn't there a danger of that word becoming meaningless?
Right. So the word universe does mean all the mass and energy and everything there is. And it implies one thing. The universe, the word implies one entity. And we have no evidence that there's anything other than the space-time we inhabit. And we see it to be expanding, and so we can project an origin for the space and time we occupy. And that back projection to an initial singularity does not require reference to an external state. So you don't have to posit that the universe exists in a larger construct for the concept to work. And so in a sense, the word universe is consistent because it just relates to all the space and time and matter and energy we can observe. And we don't know how to observe beyond that, so universe still works as a term.
The next question is from one of our live participants. Does the existence of our universe based on matter imply that there is an equal and opposite antimatter universe?
No, we were talking at the beginning about theories of where the asymmetry that led to the mass of the universe being matter rather than antimatter came from. And so we have ideas of how that might have arisen, this asymmetry, the fact that there's hardly any antimatter in the universe. You do not need to posit that there's an antimatter universe out there to balance it out, because the asymmetry from an initial state of almost perfect balance between matter and antimatter could have arisen from the laws of physics, especially grand unified theories that unite all the laws of physics. And so there's no need to appeal to an external construct of an anti-universe.
The next question is from Faisal, who asks, are there specific characteristics that intelligent creatures must possess if they exist? Must their brains be like those of humans? Could they be similar size, or could they be microscopic and still be intelligent?
It's a good question, of course. We'd love to know the answer. So we haven't found life beyond Earth of any kind, and we imagine most life in the universe will be microbial rather than intelligent. So speculating about intelligent life is very far beyond where we are in our science right now. We know there are different modalities of intelligence on Earth, for example. Intelligence exists in apes, in marine mammals, and in certain creatures on the Earth. And then we don't know nearly enough about how life evolves intelligence in a general case to speculate about what brains might be like. But yes, it's entirely conceivable that brains could exist on a much smaller scale. At a sort of very minor sense, people who study birds, intelligent birds, corvids, the corvid family, which includes crows and ravens, the neuroscientists who study their brains have understood by looking detailed at the wiring of those brains that the wiring density, the neuronal pathways of bird brains are 10 or 20 times denser than primate brains or human brains. And so it's entirely possible to have a sort of brain architecture that's more miniaturized, if you like, or more compact than a human brain. And that's just on the Earth. Out there in the universe, who knows? So it's a very interesting thing to speculate about. We'd love to have some insight on that, but until we find life beyond Earth, and hopefully intelligent life beyond Earth, it'll just remain speculation.
Excellent, thank you. It is 10:59, so we are going to wrap it up with one final question for today, and this will be the last one. The question is from Angelo, who's on with us live. Hi, Professor Impey. Is it possible that the gas giants in our solar system migrated or would migrate inwards closer to Mars or Earth orbits?
We know that planet migration is a phenomenon of solar systems in general. That's now been proven with the observation of exoplanets, especially hot Jupiters, which were among the first exoplanets to be found, where we know they could not have possibly formed at their positions so close to the star. There was just not enough material to make a giant planet that close. So we know that planets migrate from observations of exoplanets, and we have pretty good evidence in the solar system from times billions of years ago that the planets in our solar system not always been in the same places, that they migrated from further out, that two of them swapped positions, and that these had impacts on the terrestrial inner planets. Going forward, running simulations of our solar system, it is long-term stable in the sense that the orbits of the planets are not likely to change significantly over a few 100 million years. But if you play forward billions of years, it's also possible that instabilities may kick in such that the giant planets will once again migrate and possibly eject one or more planets from the interior part of the solar system, including the Earth, which would be quite a problem for the Earth. But that's very uncertain because playing forward simulations based on the initial conditions mean that changing the initial conditions slightly changes the outcome. So these are just very broad scenarios. They're not really prescriptions of what we think is actually going to happen in the solar system. But planet migration is a general feature of solar systems in the universe. Thanks for all your questions. Good questions as always, from covering the full range of astronomy. And don't remember what our next one planned is, but we'll be back doing this again in a week or so.
Yep, it's going to be in 2 weeks on July 31st. Will be our next live session. For those of you who are still around, could you hit that like button, the thumbs up? That helps us get the word out about these live sessions to other people when they see it. If you have not already, make sure you subscribe to our YouTube channel. Then you'll hear about all of our upcoming live sessions. So we look forward to seeing you back here in a couple of weeks. Thank you all very much for joining us, and we hope you have a good rest of your week. Take care, everyone.